这个很开心同学可以来到线上哈。那我们今天呢有非常重要的贵宾啊，这个有朋自远方线上而来啊，是我们一直在提的一个算是一个新的这个区块链的应用的方式，叫做 Hypercerts。那 Hypercerts 呢，其实某种程度呢也由 g0v或者是数位部的多元宇宙科也都有在研究，有可能会是一些新的结合社会运作的区块链应用的方式。所以接下来的时间呢，我想我们先交给我们的这个课程策展人 Noah， 让 Noah 呢来跟我们介绍一下今天呢我们非常难得的邀请他们上线的这个 Hypercerts 的团队，也是 Protocol Labs 的团队，他们刚参加完这个全球最大的区块链应用这个所谓的去中心化应用的一个算是一个全球性的活动，叫做Stanford。那非常难得的可以让他们在这边跟大家介绍一下他们正在开发的事情，以及从他们的观点来看的区块链的一些基础的介绍跟去中心化应用程式的 Basics。好，那我们把时间交给 Noah。
So a short introduction to Protocol Labs to Hypercerts. So basically, I met these guys last July in New York. So they were hosting this conference called Finding the Commons. I do believe this is one of the very first event or conference that's basically talking about the intersection between Web3 blockchain and social good and commons, basically. So these people are definitely one of the pioneers when it comes to social goods and to mechanism design and to the commons public goods area in the entire world, right? So a little short introduction to every one of them. So Carl basically, he was at some point building a startup that joined Y Combinator. He was previously at the biggest crypto donation platform, Gitcoin, in basically in the entire world. And then now he's running operations at Protocol Labs at Hypercerts Foundation. So first of all, welcome, Carl. Hoka, I did meet Hoka in New York that time, and Hoka was part of Unis social business at some point, and he also taught at Stanford University, and now he's also building. I do believe, Hoka, you were the one who came up with the Hypercerts idea, right?
So the original idea comes from Davidat, also a research scientist at Protocol Labs, and then I basically developed it further from his ideas and with him and with the team.
Noted. Wonderful. And the last person to introduce is the mastermind between all the coding, all the infrastructure of this is Raymond. This is actually the first time I'm meeting Raymond. But Raymond used to be I think he used to work at Google, and he also taught at University of San Francisco at some point, maybe still, and then now at Protocol Labs building for Hypercerts. The introduction are all right? So just making sure. I'm not very good at making introductions for others. But is there something you guys want to add, or something you guys want to share before Raymond starts?
Maybe just we are very excited about being here, and also about like the interest in Hypercerts in general. So thank you for having us, and thank you for the kind introduction. And it was just like a pleasure also to meeting you in New York. And I think it's like so far like our cooperation also has been like super interesting, super fruitful, and we are looking forward to more to come. And now interested in also teaching a little bit about like what our vision behind Hypercerts is. So yeah, that's so much from our side as an introduction, maybe.
Yeah, and thank you so much for making the time. I understand that Denver must be very crazy for you guys too. My understanding is you guys made an announcement at ETH Denver, but thank you guys so much for being here. I'll just let Raymond take over. And
one more thing. Sorry. So I just forgot to introduce myself. I'm the host and the professor here in this class. And we're the class in National Taiwan University. Is one of the best university in Taiwan. And our class is co-host in the Department of Computer Science and also the Graduate Institute of Networking and Multimedia. So half of the audience and the students are from the computer science, and half of the student has a computer science background, but in the other Graduate Institute of Networking and Multimedia. So they are, most of them are top-notch engineer or like a kind of a technology background. So if you want to share more on the technology part or the programming part is fine. However, some people may just want to know the basics because they just start to learn the basics about the blockchain or the dApps. So both the basics or advanced content are welcome for this class. Yeah. Okay. So Noah, back to you. Yeah.
So Raymond, just take the stage. Go ahead, please.
Yeah. Thanks for having me. I love teaching. It's one of the reasons why I do still teach at University of San Francisco every once in a while. And these slides, they're a little outdated. This is slides that I used to teach a blockchain class at UC Berkeley probably 5 years ago. So if there's anything outdated, I apologize. It's probably mostly right, but feel free to raise your hand and ask questions. I also want to make this more interactive because I don't have a good grasp of what people know and don't know. So if there's anything that I'm saying that's too fast, please stop me. I love teaching, so happy to slow down and explain things further. Let me give a quick summary of where we're going to go at a high level. So just a quick overview of today. We'll try to leave a lot of time for breaks, but I'm going to go over blockchain basics for about 30 minutes. This is to go over just how blockchains work, what's the programming model, what are the types of things you want to think about when you're programming smart contracts, and what are the good use cases for smart contracts, just at a high level, just so that we're on the same page. And then I'll spend about 20 minutes going over the Hypercert smart contracts in a little bit more detail. You guys can see real live Solidity code that's currently deployed on I guess Optimism and Gurley. Then Carl will spend about 20 minutes talking about how we're currently thinking about Hypercerts and the intersection with other protocols and other funding mechanisms. And then Holke, our visionary, will give a high-level overview of where we're going to go from here, because we're just in the beginning of our journey. And then we want to leave plenty of time for questions, but don't feel obligated to wait to the end. Like I much prefer it if people ask questions in the middle as we're going. So let me skip over to the blockchain basics. Yeah, I'm going to go over smart contracts. These slide decks were done in collaboration with some other professors at UIUC, NYU, Cornell. So this has been tested in a number of different universities. But at a high level, I think one of the things that's most interesting about blockchains is just how diverse it's getting. If you look back 10 years ago, it really was just 90+% Bitcoin. And now we're in a world where, through the ICO boom in 2017, 2018, we were wondering, is there really legs to building crypto assets outside of Bitcoin? And I think the answer now is a resounding yes. We are starting to build much more advanced applications on top of blockchains. And you see that kind of reflected in CoinMarketCap, where many of the top cryptocurrencies today are not actually their own blockchain. They're not actually its own decentralized network. Many of these are just smart contracts built on top of other blockchain platforms like Ethereum. Today, we're going to go over, it's going to be more of an Ethereum-centric class, but at the high level, many of the concepts that I'm going to go over equally apply to other layer 1 blockchain projects like, Solana, Polkadot, any of these existing layer 1s will probably have similar programming models. So don't get too caught up on the Ethereum specific lingo, but they were one of the first to come up with smart contracts. So it's easy to start with them. At a high level, what do I mean when I say smart contracts? Well, let's take a quick step back and ask ourselves, what are we expecting from contracts in general? All they are some language to specify terms of an agreement, some way to specify who you are, your identity, and your consent into this agreement, and then some automated mechanism for enforcement and dispute resolution. That's at a high level what we expect from contracts in the real world, in legalese. And it's the same set of guarantees that we expect from smart contracts in programming setting. So at a high level, a smart contract really is no more than a simple user-defined program that runs on top of a blockchain. At a high level, it simulates a trusted third party with shared state and is often used to intermediate financial transactions. So, there might be some money, there might be some data that you are passing in and out into a function call that's going to run on chain. That smart contract in the blockchain will have some code associated with how some storage and state associated with it. But at a high level, when you take a look at how decentralized applications are built, at least architecturally, not that different from other types of cloud applications or other types of trusted third parties. The main thing that's different is that the programming languages look a little bit different. Historically, smart contracts were conceptualized back in 1994. Historically, I think the examples that they used were like, imagine if you had liens or loans and minimizing the need for trusted third parties. It's been a really interesting evolution since then, but a lot of the core concepts are still similar. So let's think about why we need trusted third parties. And I'm going to start with a really simple example of the problem of fair exchange. Let's imagine there's Alice and Bob, and Alice has $20,000 and Bob has 10 shares of Google, and they want to exchange it with each other under some condition. So let's say they only want to make the trade if Google reaches $2,000 by a specific time frame. Here's an example of how these slides are really old. By 2019. Let's imagine some date in the future, so 2030 or something like that. How do we create a system by which we can actually enforce this contract? Well, of course, you could have a legal contract and go to the courts, but we'd love to come up with some programmatic mechanism and technical mechanism to make this happen. So why is this problematic? Well, if Alice gives $20,000 to Bob early, we don't know that Bob is going to give that money back if it doesn't reach that price. And if they exchange later, as in if the price goes to $3,000, well, how do we know that Bob is actually going to give up his 10 shares of Google? In this case, it's worth even more than $20,000. So there's this problem of enforcing a contract and enforcing a commitment into the future. So what we really want is some form of trusted third party, some virtual trusted third party that is a program that can actually make this happen. And traditionally, we think about doing these things in the cloud. You might have some kind of cloud server that's responsible for escrowing and holding these contracts, holding onto the financial instruments like the money and the shares, and doing this programmatically if you want. The problem with this, and why do we want blockchains at all, is that, well, it's not that crazy to think that these cloud systems can't actually be trusted, and you don't have to look that much further than cryptocurrency exchanges themselves. There are many examples of this in historical context. The first of which being Mt. Gox, where there's been a lot of some would say unscrupulous behavior of how people were operating these exchanges. But if you deposit money into a cloud server and the owner of that cloud server or the owner of that exchange is, let's say, untrustworthy, then they could run, this third party could run off with all of your money, which is unfortunately something that happens way more often than you would think. So, there's this example of Mt. Gox. If you've been reading the news, there's the example of FTX, which is very recent, only in the last few months, where we're talking about billions of customer funds being misappropriated, allegedly used in inappropriate ways. The idea of a trustworthy third party is incredibly important, but incredibly hard to do in a traditional cloud setting, because whoever runs that server can do whatever they want. And so obviously I'm not going to go through all of these, but plenty of historical examples where you can't actually trust third parties to not run away with all of your money. And so the first most important thing that we want out of a blockchain system is that it must enforce correct execution. It can't be the case that a user expects a program to do something, but it does something else, like give the founder or the owner of this, cloud server all of the money that they can steal and run away with. So this is what I would call computational integrity. Nobody can single-handedly change how the program behaves for nefarious reasons. And in a centralized setting, that power is entirely in the hands of a service operator. I'm not going to go into details just due to lack of time. In the Q&A section, I spent a lot of time working in decentralized distributed systems. So if you want to know how consensus algorithms work, we can go into more detail then. But at a high level, the thing that is really, really cool, in my opinion, about blockchains is that even if some portion of the network behaves maliciously, let's say in this example, up to half, your program is going to be executed in the case of Ethereum on many thousands, replicated across a network of many thousands of machines. And even if, individual miners are acting maliciously and trying to steal your money or falsify records or this or that, you have a broader trust network that is going to catch that behavior, potentially punish them, and enforce correct execution. So that is an incredibly cool idea, something that you wouldn't get with just cloud servers. Because of that, financial applications are definitely the first killer use case for smart contracts. Anything from tokens to lotteries to insurance, marketplaces, cryptocurrency exchanges, identity management, covenants, commitments, sharing economy, all sorts of financial commitments and financial contracts that you would typically do using legal contracts, we can now actually program in a programming language on top of a blockchain. Incredibly cool. Just to give you a little bit of pseudocode, to give you before we jump directly into Solidity code, just wanted to give a quick example of what a smart contract might look like. So this is just pseudocode, this is not Solidity, but a token contract really is one of the simplest contracts you can think of. This is what it looks like. You might initialize a token contract where you give the creator, a fixed supply, say 1 million tokens, and you just have a function that says transferring from this person to the other person, assert that the person sending the money has enough, then deduct it from the sender, give it to the receiver, and that's it. So token contracts, you can take a look at what are called ERC20. The reference implementation for ERC20 contracts is not that much in terms of lines of code. It's probably close to 100 or so, mostly comments, honestly. And you can just see exactly how these token and token currencies are generated. Super easy. The other thing that smart contracts have to do is they have to be, technically we call this atomic transactions. The informal way to describe this is all or nothing. So, which is to say, if a user makes a remote function call to call a particular method or function inside the smart contract, either the entire transaction needs to pass, or you have to revert back to the state as if I never called it at all. Due to lack of time, I'll leave it up to you guys to think a little bit about what could go wrong. But imagine a lottery contract where you have this ticket purchase function. So if a user wants to buy a ticket for this lottery, and this is the method or the pseudocode that you would use to determine how much money goes into the pot, how much money is deducted from my balance. think about all the things that could go wrong if you don't have atomic transactions, right? It has to be all or nothing. It can't be the case that I deduct something from my balance and it doesn't actually go into the pot, or vice versa. So atomic transactions are another guarantee that you get from smart contract platforms. And you get the guarantee that they're enforced by the blockchain. That's a little bit too informal, I would say. One of the things that's really cool about blockchains is that it is very difficult to stop or censor transactions. You might argue whether that's actually true now with how the regulators are coming in. But for the most part, by and large, contracts are autonomous, they're self-executing, and it's not the case that even the creator of the smart contract can come in and revoke any work that's been done by a user. So this is incredibly cool. It means that, let's say, for example, I have some kind of automated insurance contract, and if there's some detection mechanism that detects if my flight is delayed, it'll give me, say $100 policy. It'll pay out $100 if my flight is delayed. It can't be the case that when the smart contract is deployed, that the insurance contract can, stop operating and ignore delays and run off with all of my money. One of the things that makes these systems autonomous is that it's not actually the person that created the contract usually that's running the network. You have this huge decentralized network that's running all of these smart contracts. So it would be impossible to stop unless the smart contract itself has some stopping code in it. But that would be something you'd be able to audit. The last property that I'm going to talk about, of course, there's probably more properties than this, but the last, I would say, significant property is that these are all public. These are decentralized networks that anybody can join. These are decentralized networks that anybody can receive the entire history of. And these are histories that the entire decentralized network agrees on or reaches consensus to. So what that means is that anybody can actually watch everything that's happening, which is terrifying from a privacy perspective. If some global surveillance wanted to come in and watch all the financial transactions, it's not a great thing. There are other protocols that we can go into that try to provide privacy preserving mechanisms for financial transactions. But it is the case that there is some ledger or some log that everybody has visibility into, which can be a good thing in terms of auditability. So that's another property. So to summarize, guaranteed, computational integrity to execute correctly, atomic transactions, an autonomous self-enforcing network that can't be stopped and is relatively uncensorable even by its creator, and a fully auditable history. These are some of the things that you are looking for when you're building on top of smart contracts. So to come back to why we call them smart contracts, if you compare and contrast traditional legal contracts with smart contracts, instead of natural language, we have code. Instead of paper signatures, we have digital signatures. Instead of judges and arbitrators, we have a decentralized platform of miners that do the verification. And we have built-in mechanisms for payment and escrow. Incredibly powerful primitive. It basically means us programmers now can build really complicated, interesting financial systems like hypercerts and impact funding systems on top of that. How are we doing on timing? So I'm going to start moving a little bit quicker because I know some of this is going to go into a lot of detail on exactly how this works. And I can, pause at any point for questions, but I'm going to try to skip over the parts that I think are less important and try to focus on the parts that are more important. So the way to think about a blockchain is a complete ordered list of inputs that the entire decentralized network agrees on. So the simplest case is Bitcoin. All it really does is it records flows of money. So Alice sends money to Bob, Bob sends money to Charlie. It's just a ordered list of all of these different transactions. And along that, you can start to compute state. right? So if Alice starts with $50 in this example, and Alice sends money to Bob, $17, you can start to create these state commitments where I can keep track of not just what's happening in my inputs, but also what does the world look like at any given point. Those are state commitments. And Ethereum, we're going to go into a little bit more detail on how Ethereum works and how Solidity works. But Ethereum is incredibly powerful because in addition to hard-coded financial transactions like you would expect in Bitcoin, you can actually start to deposit code, arbitrary code, inside these transactions and execute arbitrary function calls inside these transactions. So in Solidity, if I had to summarize Solidity in a single slide, what you really have are three things. You have states. So a state would include, an address. In that address, you can store some code, you can store some data, you can store some balance or some, Ethereum. You have inputs, which are these transactions that you send to the network. So maybe you have money that you're sending from and to an address. You might have some data if you're performing a function call, and you have some mechanism to pay for that computation, which we'll call gas, and we can go into more detail about that later. So all Ethereum is a ordered list of all of these transactions, whether it's depositing code on the blockchain or function calls that everybody needs to run. And it'll just go through this entire ordered list and execute every single piece of code in order to achieve, the current state of the world at any given time. I'm going to skip over this. Not super important how the Merkle roots work. This is just really saying that Ethereum addresses can either be accounts or contracts. So in an Ethereum world, I can create a wallet, you can create a wallet. These are called external accounts, which have some balance or some Ethereum. And then contracts, which are just code, they also have an address and can also store some Ethereum alongside the code. So that's one part that's sometimes throws people off. In Ethereum, there are three types of transactions: create, send, and call. So create, the creator will just send, the creator just deposits some code on the blockchain. That'll be your smart contract. And that's pretty much it. So that's create. Send just sends money from a sender to a receiver. So there's no code involved, but there's some transfer value that you're sending from the sender to the receiver. And then a call, you have a caller, you specify which contract you want to send that call to, and then you send your parameters or function arguments in the data field to call that function. So that's pretty much it. That's like Ethereum in a nutshell. And those are the three types of transactions you can see. Here's this is kind of silly, but it's kind of high level how it looks like. Everybody in this decentralized network will see the same exact order in which these transactions come in. So maybe you'll see, create a contract, call this contract with these inputs, call this contract with a separate set of inputs, create another contract. Everybody in this network, so we're talking about many thousands of miners or validators in this network, all see the same, all come to agreement or reach consensus on the same order of these transactions, and then executes them entirely, which is kind of crazy if you think about it. It basically means your computation is executed identically over many thousands of times over many different computers. The last thing that's important to understand about Ethereum is that you have to pay for computation because everybody orders all of the transactions and everybody computes the transactions. Computation is a scarce resource, so we have to pay for it. And that's where gas comes in. So you pay a transaction fee and then you pay for every operation. So because all miners evaluate all transactions, because all miners have to store everything, we have very limited computation and storage that we have to share across the entire network. So we have this thing called gas to make sure that programs always halt and people are paying for the computational complexity of their contracts. These gas costs are probably out of date at this point, but the high level thing that's important to understand here is that every operation, whether it's an add or multiply, some kind of storage read, some kind of storage write, they all have some fixed costs associated with it. So the way that it works is that you have this thing called start gas and gas price. When you first start and when you submit a transaction, you have to specify both of these parameters. So the gas is the unit of computation, which you kind of see from this chart, before. This is the unit of, this is how we account for the relative cost of computation. And then gas price is how much we're paying per unit gas in Ethereum for the computation. So if you multiply the two, that is how much Ethereum you need in your balance to run the computation. Because we want to be conservative here, we actually deduct the entire amount from your balance and make sure that you have it before we start. Then you start with the start gas. As you run your code, you're depleting gas. You're using your gas from your start gas. For negative values, you can get gas back. So if you delete data, you can always get gas back. But at the end, you have your remaining gas, and if you have extra, it'll return it back to your caller balance. Out of gas exceptions are terrible. So as a programmer, this is something you have to be very careful of when you're specifying your start gas. If you run out of gas in the middle of a computation, your entire transaction will revert to the state as if it never ran in the first place, but Ethereum will punish you for wasting everybody's time by still taking away your entire start gas times gas price balance. You can explore, as I mentioned in the beginning of the lecture, the entire blockchain is fully auditable and public data. So if you go to something like etherscan.io, super cool, you can go through, look at all the transactions from anywhere in the network and follow that. Architecturally, when we're building a dApp, like Hypercerts, I want to compare and contrast it to how you typically write web apps today. So in a typical web app, you have some kind of front end, maybe it's a mobile device, maybe it's a JavaScript client that runs inside the browser, but it will communicate with some trusted web server that may or may not talk to some third-party database. In the dApp world, it's really not that different. You still have some kind of client-side JavaScript code that runs inside your browser or a mobile phone. That part is no different. And when people say Web3, all they mean is there is some interface that your web app uses to communicate with Ethereum and do function calls. So instead of function calls in the cloud, you now have function calls that are running on the blockchain. In reality, that's pretty much the only difference architecturally. And so it's not that difficult to learn how to build and run dApps, especially if you have experience writing web apps in the past. So you can take a look at, for example, dApp Radar or the state of dapps.com to take a look at all sorts of different dApps that have been built. In a second, we'll go over the Hypercerts dApp and how that's constructed. The last thing I'll just briefly go over is, current limitations with Ethereum. Ethereum is not perfect. There's an ecosystem that is growing over time and evolving over time, but there are a million different problems that the community is working on. You can be helping out on one of the things that's really cool about having an open, public, decentralized network is that anybody in the community can come in and help contribute to solving some of these problems. Whether it's contracts that have bugs in them, buggy contracts are particularly problematic because you have these contracts that basically never stop now and can't be revoked. Miners can game the system and try to extract financial value out of your smart contracts. You have criminal smart contracts, which are kind of scary. You have incredibly expensive gas these days, so computation is very expensive. That speaks to scalability. There are all sorts of scalability solutions to try to increase the computational resources of the decentralized network. How do we integrate Ethereum contracts with all sorts of other systems like Web2, cloud services, and privacy is an incredibly important problem, especially since all financial data being on a public ledger is not fantastic. There are a number of people now working on privacy as well. So let me switch over to walking through the Hypercerts code. So here, I'll throw into the chat. Hypercerts is 100% open source. Everything out is on GitHub. So feel free to look, share, copy any of this code. It's a very permissive license. But if you have problems, feel free to file issues and contribute as well. We like working in the public, and we'd love to engage with the community as well. You'll see in our code base that we have quite a few different components. So contracts is where you'll find our smart contracts. Let me open up that in a second tab. We also have a DApp, which you can find in front end. That's here. And I can demo some of the work that we're doing. Let me switch networks real quick. I can show you some of the code in the front end and how that interacts with smart contract. We also have an SDK, which I can go into a little bit more detail. And then there's a couple other, third-party services that I probably wouldn't worry about too much during this lecture due to lack of time. But we use the graph for indexing. We use Defender to run scripts that trigger based on certain smart contract events, and of course proxy. So those aren't as important. But let's go over some of the smart contracts. So if you go into contracts, you'll see the code base for the Solidity code in particular. All the code is under source. And if you go into source, you'll see our Hypercert minter. And this is pretty much it. So the Hypercert token is currently written in Solidity. It's all here. You'll notice that Solidity is a object-oriented language with inheritance. So you'll see that Hypercert minter here inherits from, it complies with the Hypercert token interface. It inherits from a semi-fungible 1155 token. It inherits from an allow list minter, and it inherits from a contract that gives us the ability to pause and upgrade the contract. There's some internal state. If you guys have programmed in JavaScript or Java, it probably is pretty familiar how this works. In this case, this class is just storing some set of transfer restrictions, which we have to use for regulatory compliance reasons. And I'll just go over really quickly, for example, the mint claim function. So in this example, a user might specify that they want to create a new Hypercert. If they want to create a new Hypercert, they specify their account. They specify how many units of the Hypercert they want to mint. They specify a URI to some metadata that might include information about the Hypercert. Carl will probably go into a little bit more detail about what the metadata looks like, but it will include things like when the work was done, the impact of the work, who are the contributors to the work. All of that is stored not in the smart contract, but in some form of off-chain storage, whether it's IPFS or the cloud. And then we just have this URI pointer reference to the metadata. And last but not least, again, due to regulatory reasons, we have this transfer restriction parameter, which allows us to prevent users from, selling Hypercerts if we don't want them to. That will store the type restrictions, and it will call mint new type with token. And because this is inheriting from semi-fungible 1155, I can go into that code and show you this is just a general purpose token contract that gives you the ability to, when we say semi-fungible, it basically means it is both fungible and non. It has both fungible and non-fungible properties. A non-fungible token, like an NFT, is typically what people think about when they think about something with unique properties. So you might have heard of people selling NFTs like images on platforms like OpenSea. Because it has these non-fungible parameters and metadata, we can store information about the hypercert, like all the different impact claims or all the different contributors. All of that can be part of the token itself. But it also is fungible or semi-fungible in a way, in the sense that any particular hypercert can also have value. Like you could own 50% of a hypercert, you could own 70% of a hypercert. That value is encoded in the units, and that's something that's not typically supported in an NFT contract like a 721, where you either own the entire NFT or not. There's no way to break up an NFT into shares of ownership. So that's one of the reasons why we use this semi-fungible 1155. It gives us the ability to have kind of the best of both worlds, where I have a value, I can sell shares of that, but I also can treat it similarly to an NFT. The semi-fungible 1155 is a lot longer. It's a little bit more complicated, but I can go over a high level. What are the things that we're doing here? So for example, we're storing the owner of any particular token. These mappings are basically, you can think of them as hash maps or dictionaries, but it maps, for any particular token ID, what is the address that owns it. In this case, we're also storing the original creators of the hypercert. For any particular, hypercert ID, we can get the address of the owner. We're storing separately for any particular token ID how much value is associated with it. And I'm going to skip over some of the other details that may probably only be confusing at this point. We have this ability to create a token type. So in order to create a new hypercert, all I'm really saying is, create a new type ID. In this case, we effectively treat the type ID like the hypercert ID. It's just a monotonically incrementing counter. We store who created it. We store how many units of value we want to associate with it. We kind of let the creator decide how many units are associated, but it could be 100, it could be 10,000. It's just at what granularity do you want to break up the shares of this hypercert? We store the URI to the metadata, and then we emit an event that lets the world know that we just minted a hypercert, and that's pretty much it. I don't want to go into all the detail line by line of the smart contract. If you guys have questions, I'll definitely hang around for questions afterwards, but maybe I'll take a quick second to just transition over to Carl and let him talk a little bit more about how we actually use hypercerts in practice.